Alex. Today, I'm going to discuss the discrete element method within Simcenter STAR-CCM Plus and present a demo example for us to really understand the workflows and the capabilities. Okay, a brief overview of what we're going to talk about today. The first part of the presentation is going to focus on company background, challenges in the business, on the business side, and high-level solutions. Then we're going to drill in to the multi-phase capabilities and specifically the DEM method within STAR-CCM Plus. And then the third part, I'm going to present a simple demonstration problem. Okay, a little bit about me. My name is Ted Blow, and my background is in CFD. We've done several projects for customers in the aerospace industry. I am particularly interested in design exploration, multi-phase flow, and conjugate heat transfer. So if there's anything you would like to talk to me about, please let me know. Like Alex said, SDA software, which specializes in simulation, specifically FEA and CFD, has merged with Swoosh Technologies, an industry leader in manufacturing, design, and PLM. So we're able to collaborate effectively, and this is really exciting for both companies. Okay, so today we're going to be talking about CFD, multi-phase and CFD. We've done several projects, one in the both in the aerospace industry. The flying ship specifically uses a multi-phase approach of a seaplane and takeoff. This uses a VOF model where we have a virtual disk modeling the propulsion, and that was a really fun project. Okay, let's talk about how CFD and simulation is used today. Like the status quo is that our simulation models have been used to create virtual prototypes or virtual wind tunnels or virtual spaces of our engineering problem, and they kind of stand as a siloed solution. And this has been like over 30 years of a proven track record. But looking into the future, we want to use our simulation tools as design tools to front load engineering insights so that we can reduce our time to market, reduce defects, and increase product performance. And we do that by implementing a workflow and optimization tool called HEEDS, which is built into STAR-CCM Plus. But this kind of is the next generation or the next iteration of leveraging simulation tools. Okay, high-level CFD solutions. We understand that there's not one size fits all, and these are kind of the solutions that are within the portfolio and who they're for. So there's Flow EFD, which is made for design engineers to front load preliminary CFD insights. It's very lightweight. It's an add-on to the CAD tool and has basic CFD capabilities. So that's really made for design engineers. There's Simcenter Flowtherm, which is made specifically for the electronics cooling industry. It has plug-and-play capabilities with library of components. Simcenter 3D has a couple of very interesting thermal solutions, especially for space systems. And then the flagship CFD tool is STAR-CCM Plus, and this is the general purpose CFD tool capable of advanced multi-physics. I mean, today we're really going to dive into this with multi-phase flow models, specifically DEM. And so these are the CFD solutions. Who is made for what? Like I said, FlowEFD is made for design engineers, whereas STAR-CCM Plus, a general purpose advanced multi-physics CFD tool, is made for an analyst or researcher. Why is that? Well, FlowEFD is very lightweight. You don't need HPC. You don't need to be a CFD expert, and it's very fast in terms of running, meshing, training. But the trade-off is it can't model advanced physics. It cannot model the complexity of a wide range of CFD problems. With STAR-CCM Plus, a traditional CFD or a general purpose CFD solution, it can model the complexity because it can model a wide range of CFD problems. Now, the trade-off is that you do need a CFD expert, you do need dedicated HPC resources, and it really is its own vertical in that it takes more time to create, run, and understand the problem. But you do have more capability in what you can accomplish. And we work with a lot of customers who, fit into different categories, and this is just kind of a high-level takeaway. Now, specifically, STAR-CCM Plus, what really distinguishes it or separates it in industry is the tightly integrated CFD workflows, where you can perform the CAD cleanup, meshing, setting up the physics, solving, and post-processing, and iterating from one design to the next, all within the same application, all within the same license. And it's made for running through these different CFD workflows so that you can evaluate different designs, evaluate different configurations based off of the same CFD template that you would create. Like I said, it's made for design exploration. Typically, what this means in a production case is that you want to modify different geometric parameters of your problem. You want to modify different boundary conditions. You want to modify different inputs so that you can understand the design space through your simulation tool. Scalability, like I said, STAR-CCM Plus is a general purpose CFD tool, and it does take a lot of computational resources to run production cases. Like, for example, this automotive has 106 million cells, which is significant. It's not unheard of. I think it's reasonable for a production problem, but it does require dedicated high-performance computing resources, and STAR-CCM Plus does scale. So as you increase the number, of course, you do get significant speed up. So you're not hitting a ceiling in terms of the capability or the scalability. Also, I want to highlight, in the latest version, 2602, Siemens has really leaned in to GPU computation before, like the GPU compatibility matrix, meaning the models and reports available for GPU runs was very limited, but they've significantly expanded that and even into the multi-phase realm, which is significant because of the inherent challenges associated with that. So it's very exciting for speed up. Licensing, these are the on-premise licenses, the traditional. There's not one size fits all, so there's various options depending on what your need is, whether it's sporadic or regular use, or if you want to focus on automation. There's a lot of different on-premise licenses, and then a new licensing solution that Siemens has introduced is Simcenter X Advanced, and this is the cloud-enabled solution. And for STAR-CCM Plus, they have, in addition to this, which is the Simcenter X, which is normal, and that allows you to run your CFD simulations on the Siemens cloud. So this is an exciting new licensing solution, which gives you access to multiple tools. We could spend hours talking about this, so I don't really want to get into it, but if you're interested in this, we can talk offline. Okay, now transitioning to the second part of the presentation, which is diving into the general multi-phase models. Before we talk about multi-phase, we need to define what a phase is, and in this case, it is basically the state of matter. It's either solid, liquid, or gas. And multi-phase flow is when two or more of these phases move together or interact and are separated by distinct interfaces. And within STAR-CCM Plus, there are 8 different multi-phase models, and each are suited for a different flow regime. And these models can be combined on top of one another to cover a wider range of multi-phase applications. So these 8 multi-phase models are separated into 2 different families. And from a mathematical standpoint, the first one is the Eulerian models. And you can think of this as like a continuous phase or like a fluid, just continuous phase, where the fluid passes through fixed control volumes on the mesh, and the transport equations for mass and other variables are solved in each cell. The other family is the Lagrangian framework, and this is where phases are treated as discrete parcels, where each parcel represents multiple objects or particles, and the equations and motions are solved for each parcel to determine its trajectory, and parcels are tracked through time and space. Okay, so on the left we have the Eulerian, and on the right we have the Lagrangian. And within the Lagrangian models, we are going to focus on the DEM, or the discrete element method. And we can think of DEM as an extension of the Lagrangian framework. So traditionally, the Lagrangian multiphase model is suited for like dilute discrete phases, meaning like less than 10% of the volume loading are Lagrangian particles. And in the Lagrangian multiphase model, the particle shapes are limited to spheres, and collisions are not between particles are not included. You can set a boundary condition for like a stick or a rebound with respect to walls, but it's pretty limited. And so the DEM, and this is where the DEM model comes in, because the collision between particles are considered, and you can have several different types of particle shapes. One note on DEM is that typical industry solutions for DEM are standalone. And what that means is they only solve for the DEM. And if you want to perform a combined DEM and CFD simulation, you need to include a co-simulation approach and model the CFD side on a separate solution. And when I say CFD, I mean the continuous phase. So let's go to the previous slide. So if you want to model your Lagrangian particles, your DEM particles, in a fluid or gas, for typical industry solutions, you need 2 different softwares. But within STAR-CCM Plus, they are combined in the same solution, in the same simulation. So, and I'll show, the demonstration includes this, but what that means is that in the same simulation, you can include your DEM particles and your fluid phase in the same problem. Okay, so I mentioned what separates DEM for Lagrangian multiphase is particle shape and the particle collisions. So there are 8 different particle types. The most common and lowest cost primitive is the spherical, and this is the best default for throughput and can approximate some shape effects via the rolling resistance or rolling friction. Next is the coarse grain, what we can call a Purcell sphere. And this is where one coarse grain represents many individual spherical particles as one like coarse grain. And this model or this particle type is used to cut the cost when your particle count dominates the simulation and your simulation objective is to capture the bulk trends. Next is the composite or rigid multisphere. And this is where multiple individual spheres are glued together in a rigid, unbreakable condition. And this is a way of like coarsening like a fully polyhedral cell. So this is, again, a way of lightweighting your DEM type from a polyhedral to a cheaper option. Next is the clump, which is deformable and breakable, and a combination of multiple spheres. And this is important when flexibility, damage, or fragmentation must be represented. The next type is cylindrical or a capsule, and this is another primitive that is elongated and important for higher aspect ratio particles when rotation or packing matters more than spherical approximations. Next is the polyhedral, which is another primitive type. And the polyhedral is the highest shape fidelity because you can construct it, in an arbitrary faceted way. So you can fully define the shape. It's important for packing or interlocking simulations, but the trade-off is that it's the most computationally expensive particle type. Next is the flexible fiber. And this is a bonded particle fiber representation and used for fiber transport when bending or interaction is important. And then an extension of the flexible fiber is the user-defined flexible fiber, which is useful when the basic flexible fiber needs tailoring, with respect to geometry bonding or the response. And then one final note is that if you're trying to represent a coating in a particle, like a tablet in like a pharmaceutical application, for example, this can be modeled via interaction with a passive scalar model. Okay, so there are many different particle types. And the other aspect that separates DEM from the Lagrangian multiphase is the ability to model particle collisions with themselves and with the wall. There are two types of contact families. There's the basic contact models and then the additional contact models. For your simulation, you are required to select one basic contact model, and then the additional contact models can be layered onto the basic model that you select, depending on your problem. Okay, so looking at the basic contact models, the default and most widely used is the Hertz Mindlin, and this adopts a standard no-slip elastic contact formulation. So I like a fully elastic contact is like two pool balls, colliding, where it's totally elastic and plastic deformation is negligible. When this model is selected, the rolling resistance model is automatically selected. And the rolling resistance is important when particles are not spherical, when rotation dynamics are significant, or rotational friction strongly influences particle motion, like granular flow over rough surfaces, or sticky particles, or cohesive particles. Okay, the next model is the Walton-Braun, and this model is for elastic plastic contact models, where you have plastic deformation during impact. And this is suitable for materials where a collision leads to material deformation, like grain, soybeans, or coal. The next one is the linear spring, and this is a variant of the spring dashpot model with elastic and damping forces in the normal and tangential directions. And it's useful for general elastic collisions with viscous damping. And the linear spring model is interesting because there are a couple particle types that can only be used with this basic contact model, like cylinders. And then finally, the last basic model is the user-defined contact model. And this is an advanced model that allows you to define the contact forces as a field function. And this can be a vector field function. It can be a custom physics implementation where you have a linear spring with added cohesion, or velocity dependent dissipation, or a conditional or state dependent contact behavior. And the user defined contact force is ideal for research, calibration workflows, or proprietary material models. Okay, so we've gone over the different multi-phase, what makes DEM unique to the Lagrangian multi-phase model. And another thing is that the DEM CFD coupling can be implemented using a one-way coupling or a two-way coupling. And what this means is the communication between your DEM particles and your fluid talking to each other. And this coupling enables exchange of momentum, energy, and mass between your phases. And for on the CFD side, like the continuous phase, like particle effects are entered or considered in the phase as a source term. And this becomes critical at higher solid loadings. And then for two-way coupling, it's not just fluid driving the particles, but also the particles reshaping the flow field through drag and local pressure gradients. Okay, and we're going to examine this in our demonstration problem. Another capability of DEM is the ability to interact with rigid body motion, whether that's a shaking table, a conveyor, or mixing. Mixing is interesting because you have two different regions typically. You have a static mesh that's rotating about this axis, and then outside of this region, you can't see it in this video, but it's there. You could also use an AMR approach. But basically, DEM is compatible with rigid body motion. It's compatible with overset mesh, where you have translation plus rotation. Also, I want to note that there's per phase control, and this is important for erosion. And what this means is that the boundary interaction can be set on a per phase basis. So the particles can interact with the walls in one way differently than the fluid interacting with the walls. So The takeaway from this slide is that DEM is compatible with motion of various types and interactions with boundaries and moving surfaces. So it's fully enabled. I mentioned briefly earlier that you can layer different multi-phase models. An example of this is this is a VOF simulation or example where you have a gas phase and a liquid phase separated by a sharp interface, and then your DEM particles are included as a discrete phase on top of that. So this, if you have a very challenging problem or a problem where you need to model the complexity, STAR-CCM Plus is made so that the different solvers can interact with one another. Simulation speedup is a pretty big concern with DEM simulation because of the added computational cost of modeling the DEM phase, especially when you have very high particle loading. There's different techniques and options. Like, for example, there's two different particle types that I mentioned before. Let me just go back to that slide. This composite, the rigid unbreakable, is a coarse option for polyhedral. The coarse grain is a coarse option for spherical. So, I mean, clumps could be a coarse option for fibers. I mean, so there are inherently, different options for speeding up the simulation. But, this is a consideration, and they have kept this in mind when developing the DEM solution. Okay, third part of the presentation. We talked about the multi-phase capabilities, the DEM model within STAR-CCM Plus, but let's look at an example problem. And today we're going to look at pneumatic conveyance. And I chose this example because the one-way versus two-way coupling has a very significant effect on this, and I just wanted to showcase this for you. So first, we have our domain definition. I've highlighted a couple of geometric dimensions, different lengths and diameters. I want to define this so that we can understand that if we parametrically define our domain, we can then use these as inputs for a design optimization or exploration study so that we can explore the design space using our CFD tool. Okay, and you can create this in the 3D CAD because it's pretty basic. You can also, but typically we use the 3D CAD for CAD cleanup. Okay, moving on to the mesh, we use 2 prism layers to capture the boundary layer. I did not calibrate this, but this can be easily calibrated for your problem, and the cell count is 180,000, which is very small. We use trim mesh for the core, and then prism layers for capturing the boundary layer. Okay, basic boundary conditions. We have our gas phase, inlet at 20 meters per second. The outlet is just a pressure outlet to atmospheric pressure, and the walls are treated as no slip, which is pretty standard. And then our DEM phase is indicated by the red arrow and the red box. This is where we inject the particles. They're injected randomly inside of this box at 2 meters a second, and there's a total of 2,500 particles at all times, and we're just using the basic spherical. Okay. The first example that we're gonna look at is a one-way coupling where the continuous phase, the gas phase, influences the particles through terms such as drag and the momentum equations. However, there's no reverse effect. The particles are not talking to the fluid. I also include turbulent dispersion in this model, and this controls how turbulence in the fluid phase influences the particle motion. And the particle behavior in this application is largely driven by the gas particle interaction and the turbulence created by the bend. Okay, so here's the solution. I'm showing in this image or this video on the left, the particle velocity. So again, I'll just play this again. We can see that the particles enter, there's 2,500 particles, and they group largely at the bend. Okay, and oh, by the way, I'm using the basic contact model. Yeah, the Hertz-Mindlin no slip with rolling resistance. Okay, so we're using basic particle type, basic contact model, one-way coupling. I ran this on my computer, and on this video on the right, you can see the continuous phase, the gas phase, velocity field, and it's not changing. So the particles are being introduced, and it's not impacting the fluid field because it's a one-way coupling. I ran this on my desktop in 2 hours. Okay, very lightweight, very fast, one-way coupling. Just a note, the particle diameters has a normal distribution, meaning we have various particle sizes, and that's just a parameter I included. So in terms of the global parameter, I'm measuring pressure drop between the inlet and the outlet, and you can see that it converges very quickly to about 93 pascals. Oh, and here's a video of the different sizes of our particles, and this is for the one-way coupling. Okay. So I wanted to iterate this initial baseline simulation by enabling two-way coupling. And in this case, I call it gravel, and I just went into the multi-phase and enabled two-way coupling because the default is one-way coupling. That's the only change I made. And the difference in the solution is that the particles are now talking to the fluid phase. So the fluid phase is interacting with the particles, and the particles are now talking back to the fluid phase. So we can see qualitatively there's a significantly difference in the particle movement. So before, the majority of the particles were trapped at the bend, and in this case, a lot more have escaped to the outlet. Okay, so that's the velocity of the particles, and we can see here the fluid field is significantly impacted by the particle motion. Now, if we take a step back, the first example I ran on my computer, which is a 16-core machine, and it took about 2 hours. But this two-way coupled, I had to run on an HPC resource, a high-performance computing resource, and it took 583 core hours. So if we run this like on the cloud, it's comparing like $3.50 to $64. So it's significantly more expensive, but it's important because if we look at the pressure drop of the two-way, we can see that it slowly converges to about 300 pascals. So the one-way coupled solution produced a pressure drop of 93, and the two-way coupled produced a pressure drop of 312. So just by having that two-way coupled solution, it increases the pressure drop by 3. So if you're trying to benchmark this problem with your test facility, and you run the one-way coupled solution, and you're not you're under predicting, the two-way coupled may be necessary in order to capture the complexity of your simulation. So this just highlights the importance of identifying the physics in your problem that are most crucial for capturing the results that are important to your engineering study, and what is necessary to capture those. So, I mean, if we just go back, if we want to like reduce the cost of this two-way coupling, we could look at a different particle type to coarsen, so we're not running 2,500 particles. And that's just one example. Okay. So that's the end of my presentation. I just want to provide a high-level overview of the DEM capabilities and the different particle types, contact models, and how important understanding and modeling this problem is. So at this time, I'll take any questions or comments. Okay, well, if you do happen to have any comments, or if you want to talk, just feel free to contact us. You can go to our website, email us.